I myself have a little cold thing going on. So sorry if my voice cracks today during our meeting. We are into a different topic than what we've been in the past month or so. We've been doing some math heavy calculations, right? So now we're going to kind of transition from that and look at how that stoichiometry is applied through all the different types of chemistry that we can experience. We're going to start by looking at solutions. I want you guys to think for a minute what a solution is, right? So a solution is different than just a liquid, right? So I could have a glass of pure water, right? And let me actually share my screen with you guys so you see what I'm talking about. So we're going to do a virtual lab together today to kind of illustrate the topics in this chapter because they're really conceptual. And we want to make sure that you guys are getting a good picture in your head of what's happening on a particulate level, right? So I just shook this little shaker and you see some stuff come out of the shaker and fall into this water right here. So I'm going to reset it because I really didn't mean to do that. But anyways, we're going to look at that in a minute. So if we look at this water, it's pure. There's nothing in there except water. So if we were to draw little particles of this, it would be H2O, those little Mickey Mouse shaped molecule that's so important for life on life as we know it, right? Water is one of the most important things because it allows our body to work and to function and for our world to exist. So it's pure. This is not a solution right now. This is just a beaker of liquid water, right? It doesn't become a solution until I shake this shaker and some of that solid falls out. And what happened to the solid when we put it in here? Hopefully you see that it looks different when it's in this solution or when it interacts with this liquid than when it came out of the shaker. When it came out of the shaker, it was all lumped together. All of the little green dots were touching the little red dots and they were in this lump. But when they hit the water, something happened that allowed them to break apart and now they're flowing about freely, right? This is what happens when an ionic substance, or our general word for that, salt. So when a salt interacts with water, or it could be any polar solvent, when it interacts with our water, the water, because water is polar, it's got positive and negative ends, it actually breaks apart those ions and allows them to flow freely. And you can see our little key over here. Sodium is the tiny one, the little pink reddish one, and chloride is our bigger one. So our anion is always the bigger one. Our cation is the smaller one. And we can see they're floating around in here and they're moving freely. So think about it as our chlorine being a giant negative sign floating around in there and our sodium being a giant positive sign. So we've got lots of different positives and negatives flowing around freely. This picture right here is a beautiful example of why our ionic substances, when they're dissolved in water to make a solution, will conduct electricity, right? So we could plug this thing up and we could make this into the inside of a battery, right? Most batteries have some kind of liquid or paste on the inside that is just a solution that has these positives and negatives in there that are able to allow our electrons to flow through. So for that electricity to kind of flow through and be passed along, there has to be positives and negatives that are going to pull and push that electric charge through it. So since we have all of these ions floating around, in what we call this disassociated form. So when you disassociate from something, you remove yourself from it, right? So our ions disassociate from each other. That water allows them to do that because water's polar, it's positive and negatives, kind of push the positive and negative sodium and chlorine apart. So some parts of the water molecule will actually attract sodium ions. Some will push sodium ions away. Some parts of the water will attract the chlorine ion and some will push it away. So there's this constant dynamic process in a solution that's different than if we were to just to have this liquid water or liquid. I mean, we could even make liquid salt, right? If we melted it and heated it up enough. And that would be different than the salt when it's dissolved in water. So our salt, when it is bouncing around, in here, let's show that again. When it's bouncing around, it's not called liquid, right? Because it's not a liquid. We haven't melted it. It's not in that state of matter. The state of matter our salt is right now in its disassociated form is called aqueous. So you'll start to see the AQ in parentheses when we're looking at our chemical equations. And I'll show you guys an example of that from your textbook here in a minute. And that AQ means that our substance is dissolved in water. So it's different than a liquid state of matter. So when we have a solution, I want to make sure you guys understand the terms. We have a solute and a solvent, right? So the solute is what is dissolved, and the solvent is what does the dissolving. So our solvent is what is going to break apart those ions or surround our solute, right? So because not everything when we put it in water will break apart and disassociate. Sugar is a prime example. I know most of you guys have made sweet tea before, right? So you want to get the water all nice and hot and the tea all brewed before you put the sugar in it and give it a good stir. So our sugar is not an ionic substance. Remember, sugar's chemical formula is C6H12O6. So it's all those covalent or all those nonmetals lumped together. It's not a metal and a nonmetal. So when it is put in water, there's not enough attraction between that little polar charge on our water molecule to actually separate out the carbon from the hydrogen from the oxygen inside our molecule of glucose. So our glucose wouldn't have all of these little pieces floating around. There would be individual molecules of sugar floating around in here. So it would be all these little balls stuck together in these uniform units or uniform molecules floating around. So there wouldn't be all of these positives and negatives floating around in this kind of dynamic process to allow that electricity to flow through. So only ionic substances disassociate and can conduct electricity in the water. That's why if you read any in chapter 9, there's a big focus on predicting what will conduct electricity in water and what won't. And you need to know that our ionic substances disassociate when they are dissolved and therefore can conduct water. So water here would be our solvent. It is what is breaking apart our ion, and our salt would be our solute. So I always like to tell people, water is called the universal solvent. So water is almost always going to be our solvent. It's almost always going to be what does the dissolving. Typically, polar substances are good solvents because they have that positive and negative kind of force there to break apart and to allow things to flow through them in this form. Nonpolar things, if you want to try to dissolve something that is nonpolar, you either have to play around with some of the pressure or the temperature, or you have to try to pick a solvent that is nonpolar as well. Because we've learned already that polar things interact with polar things and nonpolar things interact with nonpolar things. So there's a little bit of care when you're picking solvents and solutes to try to get things to dissolve, and that'll come into play a little bit later on in this chapter as well. So are there any questions so far? Don't be scared to unmute yourself and ask a question. I'm sorry guys, give me a minute. My son has brought a toy. All right. Okay. So, let's see. I think I'm still sharing my PhET simulation. So, were there any questions before we move on? Great. So, let's do a little bit of some review before we move on to the next part. So, let's see. I've got some little questions for us. I don't want that in the, anyway. Here we go. Let me share with you guys. I've got some little questions for us to kind of work through. It's a PowerPoint. I've never tried to share a PowerPoint with you guys before. I don't think it's going to work. Here we go. Got my whole screen with you guys. Let's see. Oh. Can you guys see my PowerPoint? Anybody there? Can you see it, Janie? Maybe not. Okay, well, we're going to go over these questions. If you guys can't see it and y'all don't know what I'm talking about, just let me know. We want to know which is the formula for the compound made from M. So that would be manganese, if I'm not mistaken. And nitrogen with a charge of -2. So let's remind ourselves, because this is going to become real important when we look at our double displacement reactions later on in this chapter. We've got to know how to take our ions and make them into a correct chemical formula. So if you're looking at this, we want to know which of these is our correct chemical formula. So if we remember, this is an ionic substance because I've got some charges coming into play. And when they become a formula unit down here, when we write the formula for this, we want our charges to be equal and opposite. So if I've got M with a +1 charge and N with a -2 charge, they can't come together and be like C. C is our first incorrect answer. If we had this arrangement as 1 M and 1 N, our charges wouldn't cancel out. We would be left with a -1 charge if we took into account the charge of 1 M and 1 N, and that one can't be right. So if we look at our M2, N2, same thing. This simplifies. This is a molecular formula that can simplify, right? So C is the empirical formula of D. So if we look at this one, it's got a 1-to-1 ratio too. If we look at those charges there, they're not the same. They're not equal and opposite. So D is not a correct answer either. So we've got A and B. So if you remember, I told you guys a shortcut to writing these formulas. If you look at the charge on our anion, that becomes the number of cations that we need. And if we look at the charge on our cation, that becomes the number of anions that we need. You essentially swap these two numbers and they become the subscripts. So if I look at swapping these, my correct chemical formula would be M2, is the 2 from the N, N1, because of the 1 from the M. And I can prove that to myself. So 2 times +1 gives me +2. 1 times -2 gives me -2. +2, -2 cancel out. This formula right here gives me a 0 net charge. It's the correct arrangement. So the answer for this one is B. So look at the next one. Which is the formula for the compound made from M +3 and N minus 1. Anybody want to venture to guess what it is? Don't be shy. Okay, if we look up here, we know it can't be a 1-to-1 ratio because their charges are different. So automatically C and D are out. So we've got to decide again between A and B. If I look up here, this 3 next to my cation tells me I've got to have 3 of my anion. And this 1 on my anion tells me I need 1 of my cation. So I'm looking for a chemical formula that shows me 1 M for every 3 N. So the answer for this one would be A. My subscripts swap place, or my charges up here swap places and become my subscripts. Okay, one more before we look at a different type of problem. So, which is the formula for the compound made from M plus 3 and N minus 2? So once again, these are not equal and opposite, so they are not a 1-to-1 ratio. That automatically nixes answer choice A and answer choice D. So we're left with B and C. So let's look at our charges. This 3 right here tells me I need 3 of the opposite one, so I need 3 N's. This 2 tells me I need 2 of my opposite one, so I'm going to need 2 M's. So my correct chemical formula should be M2, N3. Hopefully these are getting easier for you guys as we go on. We'll be looking at lots more here at the end of this chapter when we talk about precipitation reactions and predicting what's going to happen when I mix 2 solutions. So let's look at this next problem. It's going to be a good one because it shows some particle diagrams. So, which is the best drawing for magnesium chloride in a water solution? And we've got our little key up here. So this Mg is my blue one. It would be my cation. Cl is the red one. It would be my anion. So if I'm looking at these pictures, is there a picture that I can automatically say, hey, it can't be that one? We want a drawing that shows it as a solution, right? So that means that this ionic substance, since it's put in a solution, it is aqueous. That means, we just saw that in my little interactive thing, that when a salt is put in water, it disassociates. So I want to find a picture up here that shows these red and yellow, red and blue particles disassociated from each other. So I see that they're not touching in answer choice A. I see that they're not touching in answer choice B. They're touching there, so they're all together in answer choice C. They're all together in answer choice D, and they're separated in E. So I can automatically look at this and know C and D are not the correct answers because they're touching each other. They're not disassociated. They are associated in C and D, and that's not what we want in the solution. So C and D are not the correct ones. So that leaves A, B, and E. How do I know which one's right? These pictures are of that formula unit. So I need to know when Mg and Cl come together, what is their ratio of ions? Or I can think about it this way. What is their chemical formula? How many magnesium ions do I have for every chlorine ion? How many chlorine ions do I need to pair with every magnesium ion? So if I look at my periodic table, I see that Mg is in column number 2. So that means that it will form a +2 charge. Chlorine is in group 7A. It's a halogen, right? It has a -1 charge when it forms an ion. So I've got a +2 and a -1. If I do my loop and swoop, or I swap the places of those charges, I'm going to need 2 red ones for every 1 blue one. So if I look at my answer choices, I need to find the one that has the appropriate ratio. For every one blue, 1 plus 2 Mg, I've got to have 2 -1 CLs. So the answer choice for this one should be E. Are there questions about any of these problems that we've worked? Okay. So, lastly, before we move on to something else, how would the drawing that we just saw change if magnesium chloride were changed to magnesium oxide? So let's look at these pictures. So instead of chlorine, we have changed this to an oxygen ion. So oxygen is in group 6A. It will have a -2 charge. So will I still need 2 red ones for every 1 blue one if this changes to oxygen? It would be a +2 to a -2. Hopefully you look at that and you see that it would be a 1-to-1 ratio. So the picture that would describe magnesium and oxygen in a solution of water would be a 1 magnesium for every 1 chlorine. So let's look at our answer choices for that one. How would the drawing change if magnesium chloride were changed to magnesium oxide? Our ratio of ions would be the same. The ratio would change to 1 magnesium for every oxide. The ratio would change to 2 magnesium for every oxide, or you would have to use different colors. Our answer for this one would be B. The ratio would change to 1 magnesium for every 1 oxide. Are there questions before we look on and look at factors that affect solubility? Great. So practically for us, we need to make sure we understand what happens when ionic substances dissolve in water, right? They don't become a liquid. They just disassociate. They just disassociate into our water like this. Okay, so not everything that is ionic is very soluble. There are some salts that are only slightly soluble. So if I look at this one is mercury bromide. It is a slightly soluble salt. So mercury and bromide, that's a metal and a non-metal. So this is an ionic substance. But if I put it in there, I see that there is some that looks kind of like it when it first came out of the salt shaker. It's just hanging out at the bottom of the beaker here. It is not disassociated like these other parts. And if you watch it, sometimes the ions change places. Sometimes they go from being stuck in this mass down here to being free in the solution. Sometimes the free ones in the solution will kind of get stuck and stick down here in this lump, right? You see those two that just kind of stuck? Let's see if we can find one that flies away. Oh, look, that one just released. Oh, but it came right back. Oh, that one did too. So what's going on here is this is showing you that every solution has a point where it is saturated, where all of our water has separated what it can separate. It can't separate anymore. Our charges are balanced. There's not enough force. There's not enough push or pull to make any more of those ions disassociate, to break that connection between the positive and negative pieces themselves, because it takes some force. Think about these like a magnet. Positives and negatives like to attract. They like to stick together. It takes energy to rip those apart. So every solution has this kind of maximum energy available to break that attraction between our ions, right? Once that tipping point has reached, no matter how much more you put in there of that salt, you're not going to get any more to dissolve and kind of lift up, right? Unless you do things we'll talk about in a minute, like change the temperature or change the pressure, right? Obviously, I can heat this solution up, and that's going to make my water particles vibrate faster. That's going to make them hit more of this stuff and apply a little bit of extra energy. So we can actually increase our solubility if we increase temperature, because we're making those particles move faster. They'll actually break apart this kind of lump at the bottom more often. So things that affect the solubility of a salt would be the strength of attraction between our ions. So if you have a really small ion with a really big ion, that big ion is going to have a big pull on that tiny one. That's going to be it's going to take a lot of energy to get those to disassociate. So typically our bigger ions, like our phosphate, or some of the ones that are lower down on the periodic table, just because they're so big, right? They have such a big pull, a big force of attraction for their ions, that the water is only able to overcome that and disassociate it just a tiny bit. We'll see some other ones up here. Phosphate. Phosphate is a polyatomic ion. It is PO4, so it's got a phosphate and 4 oxygens to it. It is very big, right? It takes a lot of energy to make that big ion move, right? So it is only slightly soluble as well. And you can see it's lumping here at the bottom. So this solution, since it can't hold anymore, and even if I add more, we'll see what happens. See how it's not breaking apart? It's just kind of sinking to the bottom, right? Going back to our sweet tea illustration from earlier. I know you guys have made tea before, and or at least my kids have. I let my daughter make sweet tea, and she was being smart and wanted it to be really sweet. So she like dumped the whole thing of sugar in there. And what happened? Only a little bit of it dissolved, and the rest sunk to the bottom and made this like syrup, tea syrup at the bottom, because that solution was what we call super saturated. So when a solution has dissolved or disassociated its maximum amount of ions or molecules, right? Like sugar, because sugar is a molecule, it's not an ion. So once it has reached its capacity and it can't hold any more, what's left just sinks to the bottom as a solid, right? So wet solid, kind of hanging out at the bottom. And we call that the saturation point, or that this solution is saturated. It can't hold any more. All the spaces in that are filled. It's kind of like a sponge, right? Sponges have holes in the middle. You can kind of think about those holes being like our availability for the salt to fit in our solution. And once all that space is filled, the rest is just going to kind of hang out on the edges. And since this solid is more dense than the liquid, it's going to sink to the bottom, right? So, and you can see this one, it's got this nice little crystal structure forming, right? So this, the way this ion comes together, because of how big it is, it's forming what we call, and what we can see here, a crystal lattice. So we would see this as a crystal on the bottom of our plate. So if you guys have ever grown crystals as the little cool kids science experiment, this is a visualization of what that experiment looks like. So we're taking our crystals and letting them slowly fall out of that solution, and they make this crystal lattice. And we see it's a repeating pattern. This one is a 1, 2, 3, 4, 5. It's a hexagon, right? So the longer we let this sit here, the bigger that crystal lattice is going to get, and the more broad it's going to get to. So if you've made those crystals before, you normally heat up the solution a whole lot. So we can make this solution hold more than it normally would if we heated it up. And in that regard, we would have a super saturated solution. So as that solution cools down, all that extra that it's holding is going to come and form this crystal lattice structure. All salts have a crystal lattice. Based on their ratio of ions, you can predict the shape of the crystal lattice. Table salt, so NaCl, has a perfectly cubic crystal lattice. If you've ever seen big salt crystals or rock salt, if you look at them closely, they're all these big giant cubes. Copper sulfate, the blue stuff that we've worked with in lab a couple times, it has a rhombus shape. So it's almost like a three-dimensional parallelogram. It looks like a little lopsided crystal. So a couple of terms that we just talked about: saturated solution, supersaturated solution, and we have an unsaturated solution. So unsaturated solution would be where we just have a little bit, where there's still space for extra to dissolve. So right now our solution of this strontium phosphate is unsaturated. If I add some more, it's probably going to reach its saturation point, and that extra is going to fall to the bottom. So let's make that happen. It's falling to the bottom. So yeah, we just made the solution saturated. If I want to make it super saturated, I've got to heat it up so that all of this junk that's hanging out down here on the bottom is able to be lifted up and disassociate. I've got to give some extra energy to that water because right now it doesn't have enough energy to accomplish the task. Okie dokie. So next, the last thing we're going to discuss today is going to be factors that affect solubility. So we've already talked about one, and that's temperature. So temperature has a huge, this crystal lattice, you can see it's really pretty now. So our biggest factor that affects our solubility is going to be temperature. Right? If we heat something up, we can actually, if it's a liquid, we can increase its solubility. The only time that gets tricky is if you have a gas, right? So gases, their solubility are when they're dissolved in something. If we heat it up, that actually makes our gas less likely to be dissolved. Now that's really different than the solid. Right? Solids have a low amount of energy, right? So we're trying to make them go from the solid state to this moving around state. And that means we have to add some energy to them. Gases already have a ton of energy. So to make them stay in one spot, like dissolved in this liquid, we have to take their energy away, right? So if we heat up a solution that has a gas in it, we're giving more energy to that solution and therefore more energy to that gas. So we're actually like hurting ourselves if we want that gas to stay in the solution because we're adding some energy, making those gas particles more likely to escape the solution and fly away. So we see this with Coca-Cola cans, like the can and even the bottle, right? If you have that bottle out and let it get room temperature, let it get real hot, like in the summer, right, when it's not cold, it goes flat way faster because any heat lets that carbonation fly away because CO2 likes to be a gas. So that's why it's important if you want your drinks, your carbonated beverages to stay carbonated longer and not get flat, you want to keep them cold. Right? You also want to keep that pressure real tight. So if you have a 2-liter bottle, if you want it to not go flat, you have to twist the cap on it a whole lot so that that pressure on the inside there stays. So if we increase the pressure, that is also going to increase our solubility, right? So we want our gas to stay in one set spot. So if we increase that push force, we actually can force our gas to stay dissolved. So if we increase pressure, our solubility of our gas will also increase. So those are our 3 biggest factors for how our solubility can be affected. So if I wanted to increase the solubility of this solution, I'd have to heat it up. If instead of a salt, this were a gas, if I heated it up, it would do the opposite of what I wanted. It would make these particles start moving around way faster and actually give them enough energy to leave my solution and fly away. Right. And let me show you a picture of what I'm talking about here. I've got another simulation for us. So this is going to visualize, it's going to be a particulate diagram of a gas. So I'm going to pump some gas in here and we can see it, it's particles. And I'm going to heat it up. So these particles are moving around. There's no rigid structure. They're hitting each other. They're transferring that energy and it's moving around. So if I wanted to make these gas particles stay in a smaller spot, see how they're like spreading out to fill their container? If I want to keep them in one spot, I have to decrease that volume, right? And what's happening to how fast they're moving? It's increasing. We see that because our pressure is going up, right? So think about that being inside a liquid. We are compressing these gas particles. They're exerting a big pressure. So if we want them to stay as a liquid, we have to do things that are going to counteract the pressure that they're exerting by pushing back on them. So if we increase that pressure, they get stuck in that liquid, in that solvent that we want them to stay in, right? So increasing pressure will increase, and I'll even show you what's going to happen, will increase how fast these things are moving. So pretend that they're dissolved in some Coca-Cola, right? I've got my bottle. I'm going to heat it up. They're moving around really, really fast. My pressure's going up and up and up until they had enough energy that they were able to fly away, right? This is also why you don't ever want to leave bottles of carbonated or cans of carbonated drinks in your car in the middle of the summer, right? They will actually get so hot that they will explode, right? Because of this pressure here. That since we increase the temperature, we decrease the solubility. So that gas wants to fly away. All that carbonation there will actually, it can become so dissolved, so undissolved from that soda bottle that it will actually make them explode. Right. So I know you guys have probably experienced something like this where you've seen a Coke can that the top of it is kind of puffed out. That's because that Coke has gotten too hot and the carbonation in there has come out of its dissolved state and it's exerted a pressure on the outside of that can. So it's kind of cool way that we all experience the chemistry that we're learning about in this chapter. So looking at that gets us about halfway through this chapter. There's not a lot in this chapter, but the most important thing will come in lab on Thursday when we look at how we measure molarity. So we're going to be measuring concentration, and we're going to be using the mole to do that. So the mole is not going to go away. Stoichiometry is not going to go away. We're just going to learn how we use properties of solutions to do stoichiometry with things that aren't solids and liquids, right? So you have that to look forward to coming up. And we will work with that, like I said, some in lab on Thursday and next class next Tuesday. So are there any questions about what it means for something to dissolve, why ionic substances conduct electricity when they're dissolved, or about the factors that affect the ability of something to dissolve? Those are the key kind of things that we talked about in our lecture today. So chime in if you've got a question. If not, we are done a few minutes early today. Any questions? Great. I will be posting your exit ticket for our topics today in just a second. So if you guys give me about 10 minutes, it should be up. And we will be ready for class on Thursday. So I'll see you guys there. If you do think of some other questions as you're working through reading the chapter or whatever, please feel free to message me either on Google Classroom or shoot me an email. I'll see you guys Thursday.
Don't you want to Beyblade? It was 9. You said just a sec.